In this lesson we're going to continue to look at the electromagnetic spectrum. In the last lessons we looked at radio waves and microwaves, and now we're going to look at infrared, visible and ultraviolet radiation together. Before we do that, we're just going to have a look to see how this type of radiation is produced. The first thing we can say is this, that all the objects around us, that's to say, in your room at the moment where you're looking, every single object around you is made of atoms, and these atoms are vibrating. And that is true of every single object which has a temperature above absolute zero. The atoms that make these objects are vibrating, and as they vibrate they emit electromagnetic radiation, and the type of electromagnetic radiation which they emit depends upon their temperature. To help us understand this, let's have a look at this light bulb filament. Okay, what I'm doing here is I'm slowly increasing the current that's passing through the filament. Now the filament might look like this under a very high powered microscope. You can see it's made of atoms, and the electric current is passing through these atoms, and as it's doing so it's causing the atoms to vibrate. The hotter the filament gets, the more the particles vibrate and the faster they vibrate. That's to say, as we heat the filament, as we heat an object, or as an object gets hotter, or as the temperature of an object increases, it's all the same thing, the atoms vibrate more, with greater amplitudes, and also they vibrate with higher frequencies. As a result of that, the frequencies of the radiation they emit also increases. So with this light bulb, where we have a low current going through this, you can't see the filament lit up at the moment. But if I were to look at this, for example, with an infrared camera, you would notice actually that the filament is glowing. A little bit like this picture of the elephant below, which is being viewed with an infrared camera. Now this shows up different temperatures in the elephant. The elephant's probably at about 30, 31, 32 degrees Celsius, its body, but it's still emitting radiation called thermal or infrared radiation, simply because the particles in its body are vibrating with a certain frequency. Now this photograph is taken at night. We can't see that radiation with our eyes because our eyes don't respond to it, but a thermal camera can detect the radiation. Now, as I increase the current flowing through the filament, what happens is the filament gets hotter, the atoms vibrate more, and they start to emit higher frequencies. So here it's emitting what we call infrared or thermal, which is invisible to our eye, but here it's beginning to emit red light. So the filament's beginning to glow red and then orange here, and it's getting a bit hotter. We've got a bigger current here and it's emitting red, orange and starting to emit a lot of yellow, and now it's beginning to emit an awful lot of yellow, and then it keeps going as it gets hotter and hotter, and eventually it starts to emit all of the colours of the visible spectrum. But of course our eyes aren't able to distinguish between these colours. We just simply mix them all together and see white light. Okay, so here the filament may be at, say, about 70 degrees Celsius. There's a very low current passing through the filament at this point, but by the time we get over to here, the temperature of the light bulb filament may be between 3 to 4,000 degrees Celsius. It was very hot indeed. So now some of the particles are vibrating around so much now in this filament, they're not only emitting all of the wavelengths of the visible spectrum, but they're actually starting to emit now ultraviolet radiation because they're vibrating around so quickly. But light bulbs don't really emit that much UV light. It's only a very small amount. If we increase the temperature still further, for example, if we get up to about 5,000 degrees Celsius, 6,000 degrees Celsius, well, that's the temperature at the surface of the sun. And by the time we get up to those sorts of temperatures, the particles there on the surface of the sun are beginning to emit quite a lot more ultraviolet radiation. So, just to summarise again, the simple fact that A body or an object has a temperature means that the particles that make it up are vibrating, which means that they are emitting electromagnetic radiation. The type of electromagnetic radiation depends upon how hot the object is. So at room temperature, for example, around about 20 to 30 degrees Celsius, objects emit radiation strongly in the infrared region of the spectrum. That's what we also call thermal radiation. But as objects start to get hotter and hotter, they then start to emit visible through to ultraviolet radiation. Very, very cold objects where the particles are vibrating around quite slowly will in fact emit radio waves and microwaves. So what are the uses of infrared and visible and ultraviolet radiation? Well, as we've seen earlier, we can use infrared thermal imaging cameras to help us see objects in the dark. Okay, so we have thermal or infrared radiation, and that's precisely the type of radiation which helps you to cook toast in the morning. Infrared radiation is emitted from nichrome wires in a toaster. As an electric current is passed through those wires, it gets hotter and it starts to emit thermal infrared radiation, which heats up and cooks your toast. The use of visible radiation is fairly obvious. It's very important to us. The cells on the retina of our eye respond to visible radiation, and it's precisely with these wavelengths that we're able to see and perceive the world around us. So these are extremely important and extremely useful to ourselves and to animals as well. Likewise, cameras and video cameras respond to visible radiation. Now, one very important use of ultraviolet radiation, for example, is in fluorescent light bulbs or energy-saving light bulbs such as these here. Okay, how do these work? Well, these are filled with a gas called argon. Let's fill it with argon. And what we're going to do to get the light bulb to emit light is we're going to pass an electric current. We're going to fire electrons really through this tube, and these electrons are going to collide with the atoms of argon gas. Now, as a result of these high energy collisions, the argon atoms vibrate in such a way that they emit only ultraviolet light. Unlike with the incandescent light bulb, where here what we do is we pass a current through a filament, and the filament just gets hotter and hotter, and the atoms in the filament start to vibrate more and more and more. And actually what happens at the end, we've got atoms vibrating with a whole range of different frequencies which are emitting from thermal right the way through to ultraviolet. Well, that's not exactly what's happening in this energy saving light bulb. Electrons or an electric current with a particular amount of energy are colliding with individual argon atoms and causing these argon atoms to vibrate in a particular way that they emit only ultraviolet light. But what happens next is that the inside of the fluorescent light bulb is coated with a special paint called a fluorescent paint, and that fluorescent paint contains things called phosphors, and when the UV light hits these phosphors, it causes them to emit the whole range of visible spectrum colours. That's to say, the phosphors emit reds, oranges, yellows through to violet light, and these colours are all mixed up, so our brain is unable to distinguish between the different colours and simply interprets that as white light.